our first talk in this seminar. So to you, Nicholas.
Okay, thank you. Thank you for asking me to talk. And also, Alex, thank you for putting together this CRG. I think it's an amazing initiative. And I was more than happy to put this talk together. I did do so in a bit of a hurry, so it might not be as polished as I would like it, but hopefully we'll find it all informative. So this is work that's based on my student Max Hennick's M.Sc thesis. Max graduated with a bachelor's degree and actually became something of an accomplished machine learning engineer. And then he wanted to do a master's degree. So I took him as a student, and we both learned an incredible amount of interesting math. So, oh, there's an introduction. Okay. So what I want to present is results from a paper called A General Theory of Convolutional Neural Networks on Homogeneous Spaces. That's a very fancy name, by Taco Cohen, Mario Geiger, and Maurice Weiler, just published in some conference proceedings. And, you know, most of the thesis involved trying to understand what they were saying in this paper and actually rewriting it in a different way, from a different perspective that was more algebraic. So I should say that you know, the big paper, the one that seemed to have a lot of traction, is this one here. It's called Group Equivariant Convolutional Networks by Cohen and Weiler. So I'm a mathematician, I'm a group theorist. I'm not really an active machine learning researcher. And let's just look at some Google Scholar profiles here. I just want to, let's look at cat pictures. That embarrassing. So this is Max Welling. He was like the supervisor of Taco Cohen. His most popular paper has almost 17,000 citations, which to me is weird because, you know, our best papers have like maybe 100 citations. So it seems like you need to do data science just to follow what's going on in machine learning. Nonetheless, so this is a very prolific author, and group equivariant neural networks is right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's number 10 in his papers. He has an H index of 78. So he has at least 78 papers of 78 citations. So the fact that this paper is number 10 in Max Weiler's bibliography, according to Google, is saying that this is quite an important result. Let's actually just look at this paper. Let's not look at this paper briefly. I'll tell you what it's about. This first one here. So yeah. So we have to talk about artificial neural networks. So this is what this is about. And I'm doing it from the point of view of someone who likes to think about functions and compositions and stuff. So Rn+1 here, we think about this as a very large you know, vector with n+1 real entries. And a deep artificial neural network is a function which is a composition of mappings of the form L1, B1, N1. Now this is like the classical deep artificial neural network. So what this is that each Li is a linear map from Rni to Rni+1. So these are just, you know, matrices, right? So we have a matrix of numbers. Each of these Bi's here is a bias, adds a bias vector. So you take a vector, you take a vector and you add to it, you know, some bias vector Bi. And each of these Ni's is something we'd call a activation function. So classically, it was a sigmoid function. And the way this is applied is if you have a vector and you hit it with a sigmoid, then you apply the function to all the entries of the vector like this. So yeah, and I don't need to give a definition of the sigmoid function. I think the only features you want to remember is that it's bounded between 0 and 1. It is differentiable, and it looks like it kind of tops out at 1 and bottoms out at 0. So you kind of want to think of this as something that is used for classification. So either you're in or you're out, and there's like an area between that is sort of ambiguous. Okay. So you can't talk about artificial neural networks without talking about handwritten digit recognition, which is the hello world of this machine learning. So the historically significant application was to recognize handwritten digits. So we can think about a handwritten digit like this one here as an array, and why 28 by 28? That's because that's what the MNIST database consists of. So this is a very famous database of training examples. So you have a digit, and it's just it's a square array of numbers, and it actually consists of 784 numbers, and you can assume that they're between 0 and 255. And the first thing you do is that you turn that square array of numbers into like a vector. And then your vector, you'd want to plug it into this function here, and it'll do things. And then the result here is going to be some number between 0 and 1. And the idea is, suppose that your neural network has a task, which is to identify the number 5. Then you plug this vector into that composite function that I had, and the result should be close to 1 if the vector came from an image representing a 5, and should be close to 0 otherwise. And the main achievement here was that one of these neural networks was created that could very successfully recognize handwritten digits. But the thing is, it consists of a bunch of matrices and a bunch of bias vectors. And these matrices and bias vectors were not actually coded by hand, but they were obtained by training. So the way this was done was that you'd have this neural network, and you'd start throwing examples of handwritten digits at it, and you would have an algorithm that over iterations would make it become more and more accurate. So, and that's what machine learning is, basically. It's designing algorithms in a way that they become better by training. So there's a lot of jargon in this field. So when I write ANN, other people will call this a fully connected neural network. But just think about this as a vanilla ANN. Just think about it as a composition of matrices, biases, nonlinearities over and over again. So a problem here is that if I take this digit 7, and if I rotate it or move it a bit, then the vector that you're going to get after altering it a little bit is going to be completely different. And the way this thing is set up, there's no reason a priori to expect that your artificial neural network will be able to tell a digit 7, this digit here, from if you just took 7 and you just sort of shifted it a little bit to the right, the vectors would be completely different, and there's no reason why you should get the same result. So one way of overcoming this difficulty is to simply train your neural network a whole bunch of perturbations of your digits, and you hope that if you do this enough, you get something that's robust. So one solution to this is to use these things called convolutional neural networks. So these things have things called convolutional layers. And if you go back to like our original image of an A and N, there's no real, the convolutional layers are just special kinds of linear maps. And what they do is that they respect the fact that your input is a rectangular array of numbers. And a convolutional layer is parameterized by a filter or a kernel. So here's an example of a rectangular array of numbers. Here's a kernel, and this is the result here. So another rectangular array of numbers. I wanted to look at some animated GIFs, but I will not because I think I might run out of time if I do this. So okay, so what we're going to do now is we're just going to get a little bit more mathematical about things. So in computer science, a rectangular array with indices I and j is just a function that takes two positive integers and it returns a number that's stored at that double index. If you wanted to, you could represent an array by a function from the integers to r. And the definition of this function would be as follows. If you plug in I and j, right, which is an element of z cross z, you'd return the value of the array. And instead of raising an index error, you could just put a 0. That's something you can do. And so the thing is, you have inputs. So an input would be something like this. This would be an input. And this is a kernel or a filter. And in both cases, we could represent these things as functions from z to z. So how would you do that? We can draw some axes here. Right? So for example, here, f of 1, 1 would be equal to 1. And here, if I put axes here, right? Here I'd have a k of, let's say, 1 k of 1 comma 2 would be equal to 0. So this value here, right? And now we can think about how this fits with group actions. So groups, what is a group? Well, I'll give an example of a group. A group would be z squared and addition. So we have vectors, and if I have vectors 1, 2, and 3, 4, I have a group operation called addition, and this would be the result of addition. I'm assuming that the audience here knows what a group is. So a group acts by symmetries on things, and in particular, a group acts on itself. So when we say group acts on itself, we mean that it acts by permutations on itself, and a group action has to obey certain axioms. Of particular interest to us, now remember, we're thinking of a computer vision application. So we have a rectangular array of images, a rectangular array of numbers that represents an image, and we think about this thing as a function from z times z to r. And now we want z times z as a group to do things to my image. So whenever you have a set of functions defined on a group, so what happened here was that now I'm thinking about my functions being defined on z plus z, the group. Then we have this thing called a left action on the functions. So if I have a function here, I can obtain a new function called the left translate of the function. And the formula for the left translate is when you plug x into the left translate, you get f of g inverse. Sorry, f of g inverse x. I'm sorry. So notice that we have a g here and we have a g inverse there. And that maybe looks a bit strange. So I'm going to go and show you an example right away, and then afterwards I'll talk about these left actions. Okay, so here's another group. It's the real numbers of plus. So here we have a function f, and here g is r, right? This is from r to r. And here's my function, f of x equals sine x. So in this particular group, elements have these things called inverses and a group multiplication. In this particular group, the inverse is taking the minus, and the multiplication operation is given by addition. This is problematic, but let's just sort of power through this. If I take the function sine, I take the element 1 inside my group G, then I can take lambda 1 of sine, so it's this thing here. And by the definition that I have, this is equal to, when I plug in x here, I get sine of minus 1 plus x. And what does that do? Here we have the graph y equals sine x, and here is a graph for lambda 1 of sine x. So we have the group element 1, which you think of as acting by translations on the real line. And the result is, if you look at the graphs, well, we get a translated sine graph. And like we have to point out to students in calculus, if you want to shift to the right, you have to subtract by 1. So this is why, you know, one of the reasons why these inverses show up here like this. The axiom of a group action is as follows. This is the axiom right here, is that if I hit f with lambda h, and then I hit the result of that with lambda g, then that should be the same thing as hitting f with lambda g times h. So here is just a careful verification that with this definition, we actually have that this is satisfied. This is surprisingly tricky. So I mean, you can look at the chain of equalities if you want, but you know, you have to apply all these things carefully, and you do actually get the desired result here. I do just want to point out stuff like, you know, GH inverse is equal to H inverse G inverse. And if that seems strange to you, then you can think about what happens when you have invertible matrices A and B. So invertible matrices form a group. And we take the inverse of that, you get B inverse A inverse. So this is the formula for the left group action on functions. And when we act on real valued functions, the left action of R shifts these functions. So we have groups, you have functions on the groups, and the group acts on the functions. Okay, so if we go back to our setting, what we were interested in was thinking about images. So an image here is a function from z squared to r. So here's an example of my image. I'm going to draw these axes again. And here I have my kernel or my filter. Now, if you look at what this picture is showing here, right? So let me just keep track of the point here. So this is 0, 0, 1, 0, 2, 0, 3, 0, 3, 1, 3, 2, 3, 3, 3, 4. If I take lambda translation by 3, 4 of this kappa, right, this is equal to, like, if you put x, y's in here, right, this would be equal to kappa of x minus 3, y minus 4. So this is just from the definition I gave you. Then the result would be to move, yeah, that's right. The result would be to move this, you know, the originally kappa, you know, its support is here, right? And what we're doing is we're moving it up to 3, 4, like that. So if we look at this factor here, right? This factor here looks like kappa or k, our filter shifted by x. Now we notice that we have these two things here that are being multiplied, right? So this thing here and that thing there. Well, what that's doing is I'm doing this times that, this times that, this times that, right? So these functions, but I have the summation here. Now the fact is, outside of the support of kappa, right, I always have zeros. So if I just look at this picture here, because k is finite, this is actually a finite sum, right? There are only finitely many values in which this first factor here is non-zero. So in the end of the day, what this says is that if I put an input x here, this is my input x, I shift my filter kappa by x, and then I do this times that plus 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 that times that plus that times that plus that times that plus that times that, and I record the value here at 1, 2, 3, 4, 1, 2, 3. Anyway, yeah. So that's a result that I get when I do this. So what this thing tells me is if I shift my filter by x and I slide my my filter over my original image, what is this dot product essentially? What we described here is a dot product, right? We do multiply a bunch of numbers and we add them together. And the idea is that, what do dot products tell us about vectors? Two vectors have a large dot product if they're similar. If the dot product is negative and large, well, that means they're opposite. So there's something to be said there. And if the vectors are orthogonal, then dot product is 0. And so you think that these vectors have nothing in common. So looking at the factors of this formula, what it's telling us is that the result of this convolution operation simply tells us, if you look at the original image, at how much the filter is activated when you shift it by this amount here. And maybe at this point it is worth showing an animated GIF because I don't know, it looks cool. Okay, so here's my image. Can everyone see this? Can people hear me actually?
Yeah,
Okay,
I can.
okay,
So,
okay, good. Right, so here you see on the left is your original image. Some people have way too much time on their hands. And you can see the filter being shifted around. And on the right, you're recording at different coordinates the activation of that filter over that patch of image, right? So it's this dot product thing. So that's really what the convolutional layer does. Convolution is equivariant. So if you transform your input, then the corresponding the output is transformed in the same way. So if you think about the original example of converting a digit, digit image to a vector, if I shift my digit image by 1 pixel to the right, the vector gets completely scrambled. If you have a convolutional layer and you have a rectangular array representing a digit, and you shift that digit by 1 pixel to the right, the result of that layer, that transformation, is going to be the thing that's translated by 1 pixel to the right again. So in this sense, you don't mess things up again. You kind of preserve that structure. Okay, and we have, and this is our definition of equivariance here. So remember, our group G does things to functions, levels of map from functions to functions. And if we do something to a function, we do something to a function, oops, and then apply L, that's the thing, same thing as applying L and then doing, making that function act on the result. Okay, so this is just the general definition of equivariance here. Although I'm afraid that it might be confusing to people because I'm using f, x, and y, but in a different context. But I just do want to give one example of equivariance, which is when your action so you have two spaces. You have x and y, and each one of these spaces has a g action. Now, sometimes G does interesting things to X, and maybe it does absolutely nothing to Y. We'd call that a trivial action. And the trivial action is an action. So an example of an equivariant map is when your target space has the trivial action, and then we set the map as G invariant. So here's an example. So f of r squared to r, right? This is just a function in two variables. And my mapping is I simply integrate this function over all of r. Now, we notice that, the integral over r squared of, let's say, lambda 1, 2, f of x, y, dx, dy, that's equal to the integral over r squared of f of x minus 1, y minus 2, dx, dy. Well, that's the same thing as this. So, transforming my input does absolutely nothing to the output. And that is exactly what I would call equivariance, where the action on the target space is the trivial action. Which is something that we ultimately want. Suppose that you had something that wanted to detect cat images, and you wanted to detect a cat even if it was translated by a certain amount. The result of your cat detector should be invariant under the action of translations. Yeah, I'm just gonna skip this part because convolutional neural networks have something called a pooling layer, and I don't want to talk about this. Just to say that convolutional neural networks are not actually equivariant, and pooling is a bit tricky to understand. Okay. So let's try and move beyond z squared. So in the big paper by Cohen and Welling, they want to consider another group of transformations, P4, which you can write as z squared semi-direct product C4. And what this is a group that is generated by z squared, which you think about as translating our image horizontally and vertically, and C4, which is the group of rotations by multiples of 90 degrees. So you want to consider a group acting on images that translates and rotates by 90 degrees. Okay, so we need to maybe just talk a bit about the algebra in P4. So any element of P4 can be written as a product of some translation times of rotation here in n is equal to 0, 1, 2, 3. And we have like some calculations. So I wanted to give some concrete examples here. So if I take the group element 1, 2 and a vector AB, then the result of 1, 2 acting on AB is A plus 1, B plus 2. And, you know, if I had alpha acting on AB, then the result of that would be, you know, the matrix that, the vector that you would get by hitting the vector AB by this matrix here, you know, cos pi over 2 sine pi over 2. I'm just going to make this a bit finer here. Minus sine pi over 2 cos pi over 2 AB. And the main feature here is, well, the main thing to be careful of is that, you know, if you first rotate and then translate, that is not the same thing as translating and then rotating, which makes things more complicated to calculate. And I can explain other reasons why this makes our life more difficult. But so this is now what we're thinking about as our group of transformations. Okay, and so originally, right, our image was a function from z squared to r. Now, what we want to do, kind of abstractly, is think about, so we have G acting on images. And what we want to have is to represent images as functions f tilde from our group G to R. Because once we have that, then, you know, we can talk about lambda G of f tilde versus f tilde. So if we're just given a function from z to r squared, so consider this cat image here. And by the way, I drew axes. And again, I just want to make it very clear that this cat image can be seen as a function from z squared to r, right? Because you see there's a little integer lattice there. And at each pixel, there's a number that's between 0 and 1, let's say, if we're rescaling it. So this really is, this cat, we can really see it as a function from z squared to r, and kind of away from the cat, right? You always have the value 0. So what we do is we make this new function from P4 to R, and we turn it into a function. We turn it into a function from P4 to R. So what we do is we take our old function f, and we want to plug in not an element of r z squared, but an element of P4. And what we do is simply take the origin, 0, 0, and look at what happens when you multiply the origin by this group element. And this works out to just f of our vector again. So, and we do the same thing for our filters. And this looks like a very fake function from G to R. But now we have something that is useful to us, because you see here, this f tilde is a function from P4 to R squared. So this implies that P4 acts on f tilde via the standard left action. Okay, so if I take alpha to be a rotation here, then by definition, it's given by this. And then something interesting happens. You see, if this is my original function, f tilde of xy, then this new function here would be lambda alpha f tilde of xy. So by doing this, we sort of turn our function to a function that's defined in our group, and the standard left action actually achieves the effect that we want. So if we want to be able to rotate images, we can sort of augment them, and we get something like this. So we can actually get rotation that didn't exist originally in the group Z squared. So let's just pretend that we had we had our f tilde, so that's our like cat image, but that's defined on P4, and standard kernel, maybe it could be like 1 2 3 4 5 6 7 8 9. Again, if you look at what we're doing here, now we're summing over all of P4. Again, if we're assuming that this kernel is finitely supported, then this is a finite sum. And what this summation here tells us, okay, so what is this? This is shift and rotate kernel by x alpha m. Notice here we have inverses that are showing up. And then we're taking again some kind of dot product against our original image. And so this cross correlation here with this formula, which is exactly like what we'd had for the original convolutional neural network, tells us how much the filter kappa tilde gets activated when it's slid over over f and shifted and rotated by this number. So what this means is that maybe your filter kappa detects I don't know, like a mouth. This is a mouth. It's a very bad mouth. Well, maybe in your picture it's a face like this. So when you use it this way, what you get is that if you look at what happens when you rotate by 90 degrees and you translate the mouth accordingly, it will record that a rotated mouth occurred at a certain spot. So this really gives us a way to record where a transform filter is activated on the image. And the resulting feature map here, so this is a feature map here. When I say psi, I mean like this. I do my best not to be jargony, but it's difficult. The feature map here now will kind of depend on both of these inputs. Okay. So we know what a rectangle, what a map from like Z squared to R looks like in a computer, right? It's just a rectangular array of numbers. Here, looking at an arbitrary function at psi, or c from P4 to R, and we see that, you know, every element in P4 can be written as a translation, will actually be a rotation followed by a translation. I'm going backwards because I'm acting on the left. And, you know, your translation, you know, is, you know, x here is given by x, y, and your rotation, you're only allowed to rotate by pi over 2. So basically, you can kind of coordinatize your group by these three indices here, right? An x value for your translation, a y value for your translation, and a rotation. So in a computer, you know, how you'd represent this is that you would have, you know, first array over here, right? So this would be like the alpha equals 0 level. Then you would have a second array here, alpha equals 1, so this would be alpha. And then, you know, so it would look like, it would be like a three-dimensional array. And in this case here, it would have 4 layers. Is there a question? So that's how you would record a function from P4 to R. And, you know, once you applied this filter to your image, then you would be able to, you know, the triple index here would sort of tell you at what rotation angle and what x and y translation would your filter be activated. Okay. So in the example of g equals z squared, and by the way, what I didn't say was that the, I should probably say this, well, we'll say it anyway. I'll just say it now. The example that we gave, this example here, we can show that it's left G equivariant. So when you take your function f and transform it by cross-correlating it with kappa to get a new function c, the result is going to be left equivariant. So the left action works in the same thing. In other words, if you take your original input, shift it by 5,2 and rotate it by 90 degrees, the resulting c will also be shifted and rotated by the same amount. So in the paper that we were looking at, this a general theory of CNNs on homogeneous spaces, the authors went crazy and said, hey, why take just a boring group like Z squared or P4? So P4 was a group that was used in their big paper. Let's just consider any kind of, you know, locally compact, well, any group acting on a locally compact Hausdorff space. And, you know, let's go wild here. And so this is what I'll be talking about now. So, you know, we already saw examples of groups Z squared and P4. These groups can be seen to be important for various kinds of machine learning tasks. For recognizing images, being equivariant to Z squared and P4 is certainly an interesting property to have. Here's another group, SO3, which is a symmetry group of the sphere in R3. It turns out that chemists are very interested in this group because maybe you want to do machine learning on chemical space. So you have a bunch of molecules and you want to, but you know, maybe a molecule is represented in your computer as being, you know, rotated in SO3. Well, you want something that would be able to detect properties of the molecule, even if it's rotated, right? I mean, it would be terrible if chemicals behave differently depending on how they were rotated. it would mean that if I lied on my side, you know, I could spontaneously combust or something, which is not good. I hope you found that joke funny. Anyway, and we can generalize P4 to SE2, which is a group of orientation preserving Euclidean transformations. And this group is like P4, but you're allowing arbitrary translations and rotations. So it gets a bit strange because this isn't really something that you can readily represent in a computer anymore. But you'd still be interested in seeing, you know, how can I transform functions on SE2 to other functions on SE2 that are still linear? So for now, what we're going to do is we're going to focus, so we're going to think about our inputs as being functions in CCG. That means functions that are defined on some group. So you give it a group element and it gives you a number, but it's only non-zero inside a compact set. So let's pretend, for example, that instead of this being z squared, this is now r squared. Okay. And now at every point in R, we have a value of our function. So this is like an analog image. Like imagine that you had a photographic film, and suppose that atoms had size 0, and you could still have an image. Then this would be like an r squared image. Now, notice though that maybe, you know, this box here is, you know, maybe this has height, you know, 10, and this has, you know, width 20. So this is a closed bounded set, and outside of that set, my function is equal to 0. So this, we could think about this as representing a function f in CC r squared, like an analog image. So we want to think about a function that takes an element f in CCG and, you know, maps it to some element L of f that's also in CCG, and you want it to be R linear. In other words, you want L of alpha f plus beta g to be equal to alpha L of f plus beta L of g. So it's like a linear map, but this thing here is now an infinite dimensional real vector space, and we have a constraint that we want linear maps that are G-equivariant. So, and we want to describe all of them. So really what our goal here is, you know, when you look at an artificial neural network, I'm going to go right back to the beginning. We had these linear functions, these bias things, and these nonlinearities, and you kept composing these over and over again. So really, we're just trying to describe what these things look like, but in an equivariant context. And so it's a math talk, right? So I'm going to almost give a proof. So consider this evaluation map. So what this is, you feed it a function, and it plugs the identity element of your group into a function. So, oops. Oh, this is right. Yeah. So now what we can do is you can have some equivariant map, and you can post-compose it with the evaluation map. Because L is linear, and due to the nature of this thing here, oh, should be a bit careful here. It's, well, I'll just go like this. This map is essentially a positive linear functional. So it's a map from CCG to R that is itself linear. And you can apply the Riesz representation theorem, which says that the value of this functional on f can also be obtained by integrating f against something called a generalized function. So in particular, any function, right, if d is actually in CCG, it's just a function, then that is an example of a generalized function. But we also want to allow things like Dirac functions, for example. So it's that's a context of Riesz representation. And here's what we get. Because we have a left action, so by definition, we have this equality here. And applying equivariance, we get that the image of L of f on G is equal to this thing here. And I just want you to notice that we have this thing here and this thing here, and we kind of moved it in and out of the L. And so by definition, we have this, we have that. And from here to here, we do a change of variables. What we do is we set zeta equals to G-C, which implies that G inverse zeta is equal to C, right? So we get this new integration here. Now, look really carefully at what's going on. This here is like my kernel, my filter, and this G inverse here is saying that I shifted my kernel by the element G. So this integral that I have here is exactly the convolutional layer that I've been showing you the whole time. And I'd like to ask you all a calculus question. So I just did a change of variables here, right? So when you do a change of variables in an integral, you got to change like your function with the new variable. You got to change your bounds of integration. Well, here it's G. What else do you need to do when you change variables? It rhymes with like Jacobian. You know, like you take the Jacobian. Am I speaking alone, or are people still here?
We can still hear you. You can take a look in the chat if you like. I think some people write in.
Okay, I can't see the chat. Okay, yeah, but yeah, so I take the Jacobian, right? So, but here, there's a special measure we can use. Mu is the Haar measure. So, and whenever you have a group, it comes equipped with a special measure that has this property that it is invariant under group translation. And this Haar measure is actually kind of unique. So, you know, the sort of deep fact from the theory of topological groups sort of just has to creep up on us. So for all this to work, you need to be entering against a Haar measure. And at the end of the day, what we get is that our equivariant linear map, any equivariant linear map, has to be a cross correlation of this form. Time's running out, but suppose I had my cat image here. So I'm going to call it C from R squared to R. And here I have my translated cat. So this would be lambda 1 C from R squared to R. Right, so you can see that I have a cat image, and I just actually, I translated it by negative that, actually. I shifted it down. Okay, just be lambda minus 1, 1 like that. I could do the integral over r squared of the Dirac function activated at 1, 1 times, so here I have C, this takes a vector as an input. And here I have the translate of this. And then, so here, this would be x inverse minus, x minus x plus c, my original cat image, c dc, here where c is in r squared. So, and in this case here, translation of an image is an equivariant, is equivariant with respect to the group. That's not usually the case. It's because our group is abelian. It's commutative. And so this is somewhat unsatisfying because it's like, okay, I have a description of all possible equivariant maps, but it involves things like cross-correlating against a Dirac function, and a Dirac function is weird. And this is actually something that me and Max ran into when reading these other papers, is that this discussion of, you know, generalized functions isn't really brought up. So, but we do have a resolution to this. So here's our approximation theorem. So Max in his thesis has something a bit more general, but this is a simpler version of this. So if G is a Lie group, I should say finite dimensional, and K is a compact set, and we have a compactly supported generalized function or distribution, and we have a compact set of functions, a compact set of functions, then instead of taking this weird generalized function here, instead of taking a weird generalized function, you can actually take a function that's infinitely differentiable. And what you get is that for every G, you are uniformly close to what's happening here. Oh, I wanted to say something. I just want to go back to this image here. So here, just like that, this translation is obtained by taking the cat image and cross-correlating it with the Dirac function at, I'm going to get this wrong, but this one here, right? So this is the new thing. And here's a sketch of the Dirac function at 1, 1. It looks like this. Put infinity there. By the way, this could be -1, -1. I'm not sure right now. This is not a function. But suppose I took an approximation of the Dirac function at 1, 1. So I'm going to try and draw like a heat map here. If I were to sketch it like this, right? So, you know, my graph would look like a you know, like a bump thing. So if I call this thing kappa, what I would get here is that kappa cross-correlated with C. What we get here would be a blurry translation. And what that means is that, you know, the better I approximate my Dirac function by a smooth bump function, the closer I get to actually realizing a true translation of my analog cat image. But yeah, but the question is, you know, can this be done in general, and, you know, what kind of bounds you can get? So a result here basically says that if you have your input sitting in a compact set of functions, then you can always uniformly approximate any one of these cross correlations, any equivariant linear map, by convolving cross correlating against an actual C infinity function. And I just want to give an example of what a compact set of functions look like. So again, suppose that you want to study analog cat images, right? So let's just take the interval 0, 1 to 0, 1, right? And you have some function f r squared to r, and it's supported inside there. So here's your image, and you have the following bounds. So you have that f of z, and both partial derivatives are all bounded by a million on the interval on the square 0, 1 to 0, 1. That's an example of a compact set of functions. And if we think about applying this to a computer vision application, this is not restrictive because ultimately you're going to pixelize your image. The values, right, like the brightness of a pixel should always be between 0 and some maximum. And between the pixels, you can assume that your function doesn't wiggle that much. So it can really bound all of these things. And the Arzelà-Scoli theorem from functional analysis tells us this is a compact a set of functions. And so I think I'm running really short on time here. So I just want to, I'm going to finish this up, but I just want to maybe talk about the proof of this. Do I want to talk about the proof? Well, I wish I would have time, but I don't. But basically, this is just standard functional analysis that tells us that we can use C infinity approximations. Normally, you can't apply uniformly because you have like this sort of weak convergence that it's called. But because you said compactness enough times, you have a uniform bound. Yeah, so I just want to finish with one thing here. See, in general, when you take when you have a neural network, right? So here's your image, and you're sort of moving your kernel around here, and this these seats here correspond to how filter 1 got activated. This is how filter 2 got activated, how filter 3 got activated. And in general, when you go from this layer to that layer, actually what you're doing here in this convolution step is that you're not only looking at one at a time, but you're actually taking a whole bunch of features taken together like that. So really what we're looking at is, in our example here, this would all be sort of, each sheet here would be an element fi in compact support over G. And this whole sort of step here would actually be given by an element, which is a vector of functions. And it turns out that the right way to look at this is to think about taking a tensor product, actually. So these are both R modules, and you tensor them together, and you get exactly this. And then the advantage is that you have some functoriality. So again, our description here is a bit more precise than what Colin and Weiler have, and it just says that any G-equivariant map like this can be approximated by a matrix of C infinity functions. So that really tells us, how to go from how to map like actual layers in a convolutional neural network to other ones. So this would be called channels here. So sort of just going back to the artificial neural network, the original one. Originally, you would feed this thing a vector that has n minus 1 entries, and you get something in R, what we can do is instead feed this thing a vector of functions, and the final output would just be some function, some final function here, because this is just isomorphic to CCG, and this would all be equivariant. Yeah, I won't quite go into this, but I'm gonna finish here with the elephants in the room. So this is all like nice. We did some math, we did some functional analysis, we had some modules, some tensor products. It was very fun, but is any of this actually useful at all? Can these cross correlations be efficiently implemented? Can multiplication in the group be done effectively? Could we make special hardware that would do this well? And in particular, cross correlation in the classically, it is done with fast Fourier transforms. Now, we know that these won't exist when groups are not abelian, not on the nose. So do we have some kind of analog, or do you have some kind of approximate fast Fourier transforms that would work well for our use cases? I didn't talk at all about backpropagation, but when you have a discrete group, like maybe G here is equal to P4, you can actually play the whole backpropagation game, and which lets us sort of train our networks. But when your group is not discrete, when you have a continuous group, you can actually take here's an example. You can actually take a loss functional here, and this gives you like some kind of image, and you can actually backpropagate this image all the way back to the beginning, the error. I mean, you calculate the error, but this error now, it's in the form of an actual image, and understanding how to interpret this error in the analog case, I think is a really interesting problem, and it's too bad I didn't have enough time to talk about it. So, and the final question is, is this actually a viable design model? Like, we can replace pooling by scaling, just by shrinking. And what if we just treat everything as images in our computer? Would this actually give us the right results? So I forgot to check how much time I had to speak, but I'm going to assume that I'm over time now. So I'm going to thank you for your attention.
Thank you very much, Nicholas, for this interesting talk. And I mean, we did run a little over time, but it's an online talk, so I guess people can come and go. And maybe you're still around for some questions. Are there any questions that you would want to ask Nicholas? I think we are so few, so if you want it, you can just unmute yourself and just ask away.
I have a question actually. In one of the very first slides where there was composition of N and B and so forth, I was lost in dimension of things because I don't know how output would be R in this situation.
Which one?
So sorry. B and L.
Here, I'll just go right to the beginning. Over this one here, right?
Right, because it seems to me that L maps to R n I plus 1, so you would be having something. Then B just shifts, so the dimension did not change. N seems also not to change the dimension. And so I'm a little bit, so it seems like you're increasing the dimension of the space by this. But at the end, you write the result is R, so that was confusing to me.
Okay, that's actually, you raise a super good point here. So in this case here, I'm not making any assumptions about these maps Li. These are just Ni plus 1 by Ni matrices. So in particular, if I were to define, N, n little l plus 1 is equal to 1, right, then this last matrix here, right, would just be like a you know, like a column matrix like that, and then I'd multiply my vector here, and the result would just be a real number.
Okay,
right?
I plus that
Yeah, maybe
I plus 1 wasn't plus 1 was in the index. It's index I plus 1.
Yes.
Okay, because I thought that you are increasing the dimension by 1, so they're making a map from Ni to something one-dimensional bigger. Okay.
Yeah.
But this is just to something else. Okay.
Yeah.
So the last map which you will have would have to map to R.
Yeah. Now, here's the thing, though. When you have the classical convolutional neural networks, right, you have these linear maps or these special convolutional layers. These don't actually decrease the dimension. And that's why, you know, when you make these, when these are done, they use these things called pooling layers that actually shrink your images at every step.
Okay, I got it. And also, if you don't mind, you showed this Google Scholar and some reference, and I just did not took time to write it down, but then I realized I'd like to write it down.
Sure.
Like this guy with a lot of references.
Yeah. So I mean, so maybe I'll just go up here. So I mean,
I see.
So Maurice Weiler was like the supervisor, and Taco Cohen was a student. Taco's, you know, PhD was on all of this stuff. So and Taco Cohen also happens to be a name that's unique and easy to remember.
Yes.
So this is very good for his scientific career. So you can look at all his papers there. Now the thing is, and I didn't get to this, you know, in their paper, A General Theory of Equivariant Neural Networks on Homogeneous Spaces, they use some pretty fancy math to describe certain phenomena. And I didn't have time to talk about this at all, but me and Max kind of found a way that's simpler, at least for us, because it's, if you know about tensor products of modules, it just is very natural. So they talk about sections and principal fiber bundles, and it's the same thing, but yeah.
Well, thank you very much.
Thank you.
I have a quick question.
Yes.
In the where you showed the convolution product, can you go to that slide, please?
Yeah. This one here?
Where you wrote the product.
Oh yeah, here. Let's go. Wait. Here. This one.
Right. Yeah, this one. So here I was a little bit confused because we are shifting the, if we shift the kernel here, it will just go to 0, 0 values, right? Don't we want to shift to the input so that we?
Yeah. Well, actually, yes. So this is I understand your confusion, and the only way to do this is to sit down and work it out. So this is explanation by intimidation, but basically, no. If this formula works, actually, no, it works. So really, what this is doing here is it is shifting the kernel, and then so like you see this picture here, we have like this you have like this pink part,
right?
So the support of the kernel is everything that's not 0. Okay, so the original kernel, its support is like the interval 0, 2 cross 0, 2, right? This is the original kernel support. Right. Now, if I take lambda 3, 4, my kernel, the support of this thing here, the support of my new shifted kernel is going to be equal to well, it's going to be 3, 5 interval 4, 6. So this pink image here, this pink box, is a support of my shifted kernel. And so this term here, right? This really is a new kernel, but instead of being supported at the original 0, it's now supported here. That's where it's non-zero. And then I multiply, so I'm multiplying the things in the kernel by these points here of my original function. Does that make a bit more sense?
Yeah, yeah. I mean, I love to check as you say.
Can I tell you? Can I share something with you?
Yes.
Okay. This is something I didn't get around to doing. We're just okay. Just give me a second. Okay, we had this left and right action here.
Right.
And I was talking about. I was going to talk about. Sorry, I want to show this thing. Wait, where's my tensor product? Right here. This tensor product. Right there. And in particular, this formula here about a right action. So I was preparing this talk last week, and it was not using the correct definition for the right action. And nothing was working at all. And it took me 4 days to figure out what I was doing wrong. So yeah, it's tricky stuff, lots of moving pieces. And yeah, so anyway, but I'll just put it back to there. So this totally works.
Yeah, right. So this this K is representing a function, like
yes,
this small kernel, right? This 3x3 kernel as a
function
from Z squared to R.
Yeah.
So my confusion was when we shifted to like a different input. So that's where I was getting confused. But probably I think you got the confusion, but I think the resolution I will check. Yeah.
Right. You're thinking about plugging in numbers where it's going to be 0 into the kernel.
Right.
Yeah. Now the left action actually shifts the function. And again, like it's the whole yoga is like given by this this formula right here. No, where's the formula? This formula right here. This is what does it. But I mean, even this chain of equalities here, Max and I had a lot of discussions about which was the right way to do this. So it is a bit tricky.
Right. Thanks.
Thanks for the question.
Thank you. I mean, I think people started to leave, so maybe unless there is any urgent last minute question, maybe we can call it a day. Thanks again, Nicholas, for giving this first interesting talk in our series.
Thank you.
Just a quick announcement. So we'll have a second talk in 2 weeks from now when Hamid Ousefi will give a talk. And as always, please feel free just to message me if you wanted to talk here as well. And I think that's it from my side. Thank you very much.
All right, thank you.
Thanks for the talk.
Thank you.
See you next time. Thank you.